Hello everyone at this afternoon session today, and I'm very pleased having been invited to be the first speaker of this talk today. And my task is to give a short introduction to the presenters, and first, very briefly to my background. I'm also an experimental economist. I did my PhD in Bonn and moved then to Cologne, and now I'm based at the Technical University of Munich, and I'm very happy to say something about the two names which are on the paper today. I think if you're behavioral economists, it's not necessary to say many words about Charlie Holt. So because when you work in this field, you stumble across his work in many corners of the field. And so I just want to say very few things. So the first is that he's really a behavioral economist in the best sense. So he typically looks at the theoretical side of behavior and markets. Specifically, he has published many papers on auction behavior, but the second side of his work, which I find really attracting, and he was one of the persons that really early started using experiments. So if you look at his publication list, which is very impressive, so one may ask, so which paper has not been published in the top 5? So he really worked a lot and dig deep into experiments, and not only for testing the theory, but also he made a lot of methodological contributions to the field, which are very important because the field is very often contested from many sides, and it's always also important to look at the methods and really critically question the methods that we use. And this is also one bit where our ways crossed. I never talked to him personally, but I worked a little bit on risk aversion and about risk determining behavior, and this is when I digged deeper into his work. So this is something that I really appreciate, that he really started already, I think, at the beginning of the 80s to run experiments and to publish really a lot of his work on experiments. So the second presenter, and I think Katri is the one who gives the presentation today, if I'm correctly informed, is Katri Sieberg. I don't know how to pronounce your name correctly, but you're based in Finland, in Tampere, and I'm always very happy to introduce someone from Finland, because I've been to Finland. I spent there also a while in Helsinki, and it's always nice I have very nice experiences with my Finnish co-authors and researchers. And she also has an experimental economics background. She has published a lot of work within the field of experimental economics. She is now interested in healthcare economics and has a position or professorship on North American studies, and is interested in how effective institutions are and how institutions emerge specifically now in the healthcare sectors. And she more specifically looks at incentives effect, which might have implications for the stakeholders and players in these markets, like doctors, patients, insurance companies, and so on. She also publishes on criminal policy and has also done something on social choice, for instance, on voting, and has also published in very renowned journals like the American Political Science Review and Games and Economic Behavior. And I'm very much looking forward to have this specific combination here for the talk today, because today it's about a paper which also directs at one point that Ken Binmore makes, that he's stating that fairness, so many things, or in many instances when we observe fair behavior, it can be explained by self-interest. So it's in the best interest of the players to be fair, and the paper today takes up this idea and tests this in the context or using the method of a modified ultimatum game. And Katri will now start and tell us what type of modifications they have implemented and what we can learn with regard to this initial statement that Binmore made. So I'm very, very happy that we have this interesting talk today, and hand over to Katri, and we will have a discussion afterwards. Thank you very much.
Thank you for that wonderful introduction. That was great. So, as you mentioned, this is joint work that I have with Charlie Holt. Charlie's been a co-author for, I just counted, over 20 years, which kind of astonishes me since I'm only 26 myself. And as you mentioned, this actually is work that looks into well, bargaining, fairness, and conflict. In particular, we touched on Ken Binmore's book, Crooked Thinking, but as you'll see throughout the entire paper, we actually borrow pretty heavily from a lot of Ken Binmore's work, and of course from other people's work as well. But some of the things that we've done in here were actually suggested by Ken Binmore on an earlier version of this paper. So in the book, which I think was presented 2 weeks ago, or there was a talk on that 2 weeks ago, Binmore explores philosophical approaches to fairness and to other actions. And as was just mentioned, the question is, are people fair because it's an inherent part of human behavior? Do people want to be fair? Or is it because they value fairness? Is it because they value fairness in itself? Because there's something that makes them want to do the right thing? Or is it because in some cases it's just strategically better for them to be fair? And towards the end of this book, Binmore argues that the latter is actually a better argument. That yes, in some cases there are reasons to be fair, but it won't always happen. And so what we did was we explored this game through a modified ultimatum game experiment. We explored this argument, and we found that our results echo his assertions, that in fact, yes, in some cases you will see people behave fairly, and even in our game, but for the most part, as people learn the game, they stop being fair. We chose the ultimatum game because it's particularly useful in the context of looking at fair behavior. It's a particularly famous game. It's famous for the simplicity of the game itself, the simplicity of the predictions, and for my interest, for the nearly constant failure of the predictions to be met in experiments, especially if you just look at the traditional ultimatum game with no adaptations. And the failure itself, instead of, I've actually heard some colleagues who don't do game theory say to me, well, yeah, but your game theory is useless. The ultimatum game has in fact demonstrated that. I actually got the master's program that I have, which is now the master's program in public policy, by arguing, no, in fact, that's not the way. We don't just end like that and say, well, ultimatum game showed that we were wrong. We're done. No more game theory for us. Let's just go back. What we do is we test it in the lab, and we test different, what could be explaining it. Is it fair behavior? Is it inequity aversion in terms of I worry about my own share? Is it threat of revenge from the person who can, reject an offer? And then we test our assumptions. So we're modifying our theories all the time, which, as was pointed out, is something that Charlie has done very nicely, and Charlie and I have worked together to do that as well. The people were so impressed here with that they said, oh, have a master's program. I saw that 2 of my students are here listening. Because I think it is really important. So I particularly like the ultimatum game as a demonstration of what game theory can do. So what's happened in the field is the failure has led to a large number of different adaptations to see what could provoke behavior that's in line with game theoretic predictions. And what we do is, in the paper, we use a number of them, not all. The literature is absolutely rich. But we use a number of them, and we provide an additional adaptation that encourages proposer demands that are in line with the predictions. But one of the things that puzzled us for a while until we explored it more concretely was that we shouldn't see in a subgame perfect Nash equilibrium behavior, you shouldn't see any rejections, but they continued. And so by exploring that, we found that it was even more interesting than we had thought to begin with. So we examined the role rejections play, and we argued that the rejections, and in our particular version of the game, there can be successful rejections and unsuccessful rejections. We argue that these can play a key role in moving proposer demands in the correct direction, and then also teaching responders when to reject and when to not reject. Altogether, the modified ultimatum game, we found, produces responses by both proposers and responders that move away from fair divisions of the resource towards the subgame perfect Nash equilibrium predictions. I should just say now, since I can't see any faces, if you have any questions, please, or comments, please just interrupt in the middle. I'm always happier that way. So I'll just go through the ultimatum game for anybody who's not familiar with it. In an ultimatum game, a proposer can decide how to allocate some pie, some amount of money. I just put, for generic purposes, 10 euros between himself or herself and a responder. If the responder accepts the division, then each party gets the proposed amount. Otherwise, each party gets nothing or some other amount as determined by the experimenters. In the subgame perfect Nash equilibrium prediction, the proposer would offer just enough to make the responder prefer to accept or make them indifferent. So say €1. There are, as has been pointed out in the literature, a number of Nash equilibria to this game, so the subgame perfect one is the minimum offer. But what's interesting, as I mentioned, is that you don't tend to see this in traditional results. Kammer points out that the vast majority of the results are between 40 to 50%. So instead of making the minimal offer and having somebody accept it, there tends to be an offer of roughly half the pie, which then is accepted. Now, obviously, people didn't just sit and say, well, okay, then we were wrong, as I mentioned. And so what I'll discuss here are just some of the ones that we looked into, and some of the more famous ones. So the first is role reversal. So role reversal is if people have the experience of playing as a proposer, then will they behave differently as a responder and vice versa. And Binmore et al. In 1985 had a two-stage ultimatum game. They had those experiments, and they had, in the first round of this, they found results that were similar to the previous one, so a tendency to be fair. But then, for the interesting aspect of the paper, they invited the responders back to play a new experiment, and they played in the role of proposers. And in that experiment, they had more gamesman-like behavior, so in their demands. And in fact, they didn't look at the responses on this one, but they absolutely behaved like a Nash equilibrium theorist would want them to. And so what we wanted to do was look at the impact that role reversal would have. Another one that we found interesting is the common expectations. Harrison and McCabe in 1996 had ultimatum games in which they had all players fill out what they would do in both roles. And they recorded responses regarding what a subject would demand in a set. So what would you demand this? Would you demand this, this? And then in many of the treatments, they were able to update and see what other players were doing. What's important in that one is that they had the potential to have either the role of the proposer or the responder selected, so it's a little bit of a built-in role reversal. But in terms of the common expectations, by actually seeing what other subjects did, they started moving their offers and what they would be willing to accept in the direction, especially in some cases, of the Nash equilibrium. So they had in one of the treatments, computer subjects, and they made Nash equilibrium demands, or they accepted Nash equilibrium offers when they were in the role of responders. And that actually, when that information was out there, sort of visible to the group, that started moving offers and demands in the theoretical direction. Yeah, and as I mentioned, they had varying levels of information given through the games to allow updating. What they found, as I mentioned, were demands and acceptance that came very close to the Nash predictions. And then another thing that's been pointed out is that competition can also produce behavior that's closer to the Nash equilibrium. Marchand and Julio showed that you can have, as competition increases, people are more and more likely to make Nash equilibrium net predicted demands and offers. And that has been pointed out in a number of papers. It doesn't necessarily conflict with fairness, but what it does is it means that somebody who might want to demand fairness finds that he or she cannot compete when other people will be willing to accept less. So our adaptation encompasses a number of those. And what we did was we had a bargaining game, so an ultimatum bargaining game, but instead of a 0-0 outcome, what we had was a conflict outcome. And this actually builds on a series of papers that we did as a part of a National Science Foundation grant. And the grant was to look into international conflict, so we had one paper on that together, but this was just more of a general game. And so, you know, in the context of the grant that we had, the adaptation is similar to either real world conflict, interstate negotiations, legal bargaining in a court, strikes. So it's a situation instead of, if there's an offer made, instead of it just going to a 0-0 outcome, as I mentioned, there's going to be a cost to both parties and one party will win all. So the proposer can decide how to allocate money between him and herself or herself and a responder. If the responder accepts the division, similar to the traditional ultimatum game, each party gets the proposed amount. Otherwise, there's costly conflict in which the winner wins the whole pie and both parties lose $2 in our particular game. And the conflict outcome is determined by a known probability that the proposer will win in the event of a conflict. And the different probabilities are our treatments. The Nash equilibrium predictions on this are that the proposer should offer just enough for the responder to accept, given the cost and given the probability of success. And of course, if everybody sees what is the appropriate amount, then conflict should be avoided. So the model, just to give a background model, this again builds on the international bargaining model of war from Powell in 1999, and he starts with an initial status quo division. It turns out, theoretically speaking and experimentally speaking, this status quo division is irrelevant, but it's important to have if you're going to actually put it into an international context, so we have kept it in. It's, you know, do you have Alsace-Lorraine or do you not at the beginning? But in the end, it really only depends on the probability of success of the proposer. So the proposer can look at his or her own probability of success, demand some amount X, and the rest goes to the other player. The responder can accept the proposed division or can reject, and a rejection leads to a conflict with a cost C in which the proposer wins the entire pie with a known probability of success. And so from this, you can do the backward induction, calculate the expected value of rejecting, and the proposer should offer just enough to make the responder indifferent or slightly prefer to accept. So the demand, what the proposer himself wants, is an increasing linear function of the proposer win probability, P, and we end up with this amount, taking into account, so the demand will take into account the cost and the probability of success. Our experiment, we just take one version of this. We had an initial pie size of $10 with an initial allocation of $3 to the proposer and $7 to the responder. The proposer makes a proposed redistribution, and we restricted this to whole numbers just for simplicity. To the responder, if the responder agrees, each player receives the respective payoffs. If the responder refuses, then each player receives a cost of 2, and the pie is divided based on the results of a 10-sided die roll. So either the responder wins the whole thing or the proposer wins, depending on the probability. So the winner would get $10 minus the cost of conflict, which is 8, and the loser would lose money. These probabilities are known the players know in advance the probability that the proposer would win, and the probabilities that we used were 0.2, 0.4, 0.6, and 0.8. And we varied them by treatment. So one treatment would have just one probability in it. And for the probabilities that we had, the predicted demands for the proposer were 3, 5, 7, and 9, respectively. So you can look at this right away and say, there's only one of these that's going to have a fair outcome. That's for the 0.4 probability. The rest of them are going to be a little different, and at least initially be a little bit upsetting to the responder or proposer. We ran the experiments at the University of Virginia. We had 72 subjects, and they were UVA undergraduates. We used Charlie Holt's V-Econ Lab bargaining game, and we selected the political conflict option for them. Each session, and these are divided into actually 2 parts, so 1 part per session had 12 subjects and had either 3 or 4 stages, depending on which part it was. So in part 1, stage 1, we had 6 of the players were proposers and 6 responders, and they played a one-shot game. We didn't tell them the order of this game, and to make sure that the proposers stayed proposers and the responders stayed responders, and then when they switched roles, switched, I actually went and logged in every single one of them individually. So yeah, they did not know the order of these treatments at all ahead of time. Stage 2 then kept the roles the same, and the subjects played 6 rounds in which the proposers were randomly matched with responders. In stage 3, the probabilities stayed the same. They were the same all the way through every treatment. The proposers and responders switched roles, and they played a one-shot game. And then in stage 4, the proposers and responders kept the new roles, and they were randomly matched for 6 rounds. So they got, in part 1 of the game, they got a thorough experience with both the role of proposer and of responder. The goals in this part of the experiment were to see the effect of learning, the effects of expectations, competition, and role reversal. In part 2, we were interested to see what would be the effect of differences in experience. Would players who knew the game behave differently, not choose the same strategies they had chosen before when they had brand new subjects to play with, or what would happen? Charlie likes quantum response equilibria a lot, and so we were looking at the effect of having inexperienced players on the strategies of initial proposers. And so what we did in this one was we kept the 6 original proposers in each treatment. We asked them to stay, and we brought in 6 brand new responders, and we announced to everybody, hey, these people have been in the game before, you people are brand new, this was common knowledge for everybody, and then we had them play the game again. So stage 5 was a one-shot game, similar to stage 1 of part 1. Stage 6 had 6-round random matching, and then instead of having another one-shot, we just had them switch roles and did random matching for stage 7. And so we could see, if you look at the first proposers for each treatment, they had every single possible experience that they could have, including inexperienced members join the game. So we were looking at, in addition to the role reversals, we wanted to see the effective experience. If you look at the results, especially in the first one shot, the blue line is the subgame perfect Nash equilibrium predictions, and as I mentioned, for a probability of 0.2, the demand should have been 3, 0.4 it should have been 5, 0.6 it should have been 7, and 0.8 it should have been 9. And if you look at what they actually demanded, it's quite different, and it looks like there's some interest in fairness. The 0.2 is too high and close to 5. 0.4 is pretty close, very, very close to 5, and the other ones are much, much lower than they should be demanding. And if you look at the spread or the variance of their demands, you can see that they're kind of all over the place. So the orange line is 0.2, and it's got some low demands, but then some up at 5, and then down, and they're all over. What's interesting is how these demands change when they go to the next part. So when you look at the average for the 6th round demands, in particular, the demands for probability 0.2 come very close to the appropriate demands, or very close to the value of 3. They're at 5 for probability 4, and they're higher, but not quite as high. And I'll just say now, at first we didn't think so much about it. We were just disturbed by the level of conflict. But if you look, I'll show you in a moment, there was a fair amount of conflict for the probability 0.2 rounds, and that got driven down. So the demands got driven down pretty sharply. So they learned through the conflict what they could or could not demand. And here, by winning in some cases of conflict in the 0.6 and 0.8, they started moving their demands up. But here in particular, they really, really learned. And as you see from the variance of the demands, now they're much more sharply focused around the Nash subgame perfect Nash equilibrium demand. And as I mentioned, the conflict for the one shot in particular, there was a really high level of conflict at the 0.2. So they were asking for 5, and the responders who were getting a demand for 5 suddenly realized probabilities on their side. And not only did they reject the demands, but you'll see later they were successful in doing so, which then drove down the demands in the random six round stage of the game, and so the conflict was able to drop. And you can see the conflict for the first one shot is higher in all stages, and it decreased in the 6th round. And also, if you just look at the average demands made in the 6th round random matchings, for the 0.2, they start off too high, go lower, try high again. The average is coming closer, as are the averages for all the others. They're still too low for the 0.8. What's really interesting is the effect of switching roles in this game. So if you look at part 1 where they switch roles, now these people have been responders in the first 2 stages of the game. And when they get the opportunity to be proposers, they go very close to the Nash equilibrium demand. So they've learned from either, they've learned in the 0.2 that they can reject it and that they shouldn't make too high of a demand. In the 0.6 and the 0.8 in particular, they've learned from from rejecting a demand and then finding themselves losing in the conflict, that a higher demand can be made in the role of proposer. And so they go much closer. The original proposers don't like that. But that conflict goes down over time. So if you look at the one-shot reverse, when they have initially reversed roles, there's some conflict at the beginning, although not so much at the 0.6. And there's still remaining conflict. This was a source of concern, and this is what I'll show in a moment. And again, this just shows the same thing, that the demands are starting to go closer and closer to the Nash subgame perfect Nash equilibrium predictions. So that was for part 1, all of these. Then, as I mentioned, in part 2, we had the original responders leave, the same proposers, they again resumed the roles of proposers, and 6 brand new people came in for each treatment. And it was announced, and what we wanted to see was, will they offer too much? Will they offer too little? Will they demand too much? How are they going to react to people who clearly don't know the game? But what was interesting in this case was the role of the conflict in particular allowed them to make demands, and with certainty that they would be able to win, or they would do well in the event of a conflict. And so if you look at the orange line again, is the part 1 one-shot when everybody was brand new to the game, and the part 2 is the one-shot with the brand new responders but experienced proposers. And again, this is close, not perfect, but closer. And that actually, interestingly, not as close as the original responders did, but it's still close to the subgame perfect Nash equilibrium demands, and the variance is quite small. And as in the 6-round random matchings, then the experienced proposers got even closer still to the subgame perfect Nash predictions. The conflicts are not surprising. In particular, the conflict rates for the probability of 0.8 are not surprising at all for the first one-shot game in part 2, because what we have here are brand new responders suddenly seeing demands between 8 and 9 out of a $10 pie and being shocked and irritated. But as you see, the conflict decreases sharply after that. So they've learned from unsuccessful conflicts that those demands can be accepted. When they switch roles, you see also the variance go down, and again, they're not so much in probability 0.6, but they're coming quite close to the Nash equilibrium predictions. There still does remain conflict. So we were really satisfied with the demands, but we were a little bit concerned about the level of conflict. So we wanted to look at this more closely and say, if you look at this gray line at the bottom, this is the predicted level of conflict for the game, and there should be 0. And so we tried to figure out what was going on with this level of conflict. So the initial implications are the combined experience with time with both roles, and with this second experiment with part 2 does produce demands that are very close to the subgame perfect Nash equilibrium predictions. As Ben Moore et al. Say, the subjects act like gamesmen, but the responses were surprising to us. So we noticed that with subjects experiencing both roles, they learn what they should demand, given the probabilities that they have, but they still tend to reject, and that leads to costly conflict. So we looked more closely into potential causes of conflict, and we thought it might be possible that probabilities could be overweighted if they're small, but this, over time, we saw that overweighting decreases. So at the beginning, we did see a little bit of this, but then we saw that everything tends to go to the subgame perfect Nash equilibrium, so the overweighting went down on both the part of the proposers and the responders. We looked into, was the expected value of conflict higher than accepting the offer, and that out of the entire game occurred only in 2 rounds. Then we thought, could this be irrational conflict? You know, is there just some fun in pressing the conflict button or rejecting button and seeing the roll of the dice, which actually occurs on there's a moment where you wait for it and then you get to see the outcome. So do they reject because that's fun? That's almost impossible to test, but what we looked at was, and again drawing from a paper by Ben Moore, do they reject offers that they themselves made? And so when we looked, here are sort of all the data, but the top one is for the game in particular. We had one and only one person ask less than the Nash equilibrium and reject less than the Nash equilibrium. So the more interesting numbers are here. You had people, the ones in black were ones who were pretty much consistent. So if they asked less than the Nash equilibrium, then they rejected an offer that was the Nash equilibrium or higher, because that did not seem correct to them. If they asked the Nash equilibrium, then rejected higher, that was also consistent behavior, and asking higher and accepting higher is also consistent. These three, with this one slightly questionable because I just put a generic category. These three categories are where people, say, asked the Nash but got mad when people rejected it, asked higher than the Nash but rejected the Nash, or asked higher than the Nash and rejected higher than the Nash. Although these asked higher and rejected higher could be more precise. So it's less than half, but it's still a decent number in part one. In part two, with experience, you see only 6 of the total actually had any tendency to ask or reject offers that they themselves would have asked for. And so the vast majority of them, in fact, were consistent in behavior. So this is not irrational rejections. They're actually using rejections when they have them to punish behavior that they don't see as suitable because they themselves didn't make it. So what we looked into then was if that's the case, then conflict is actually educating. This idea that we have conflict and this creates a bit of competition in the game, or it's not just 50-50, the outcome's not going to be fair. This can be used as a teaching tool. So and this has been explored to some extent in the literature in different ways, but it's a costly punishment. So conflict teaches proposers which demands are acceptable, and importantly, successful conflict teaches proposers to restrain demands. So I pointed out in the part of point 2, when they were making demands of roughly half the pie, successful conflict where the proposer rejected and the proposer won taught the proposers in the next few rounds to drop their offers closer to what the Nash predictions would say. Unsuccessful conflict also taught responders to stop rejecting and taught proposers that they could increase or keep the same demands. So we did a similar analysis to Grothkopp's paper, and what we looked at was the demand in one period and then the demand in the next period. And what we did was we divided this into either they had a successful demand where the demand was accepted, or it was rejected but the rejection didn't work and they ended up winning the whole entire pie. And then we looked at unsuccessful ones. And if you look at these, if they demand, now I combined all the data in here, but so you'll see some clusters around the Nash equilibria. So there's a Nash equilibrium at 3. If somebody demanded 3 in period, say 1, they were likely to continue demanding 3 in period 2, and some of them went on and demanded higher. If they demanded 4 in period 2, then some of them demanded 4 or 3 later, but frequently they would have, or just as many demanded the same amount. And you do see clusters at the Nash equilibria. So you've got people who will demand 3 in consecutive periods, people who will demand 5 in consecutive periods. Again, this looks like a fair division, so that makes sense. People who will demand 7 in consecutive periods. The 9 in part 1, not so much. Some people got really enthusiastic and went on to demand 10. You also see the effect of successful punishment. So if somebody demanded too much, say 4 in one period, that person might demand 3 in the next one, maybe 4 in the next one. If they demanded 5, they might go down to 4 if it was unsuccessful. Some of them stuck with 5. So you can see that actually there's a tendency to discourage. Somebody demanded 7 in one round, it was successfully rejected and dropped the demand to 3 in the next one. The impact of this is even more clear in part 2, which was the one with the mixed experience with the experienced proposers and inexperienced responders. And in here, you see very clear clusters at the subgame perfect Nash predictions. So 3 and 3, or these people stuck with 3 if they demanded 3. If they demanded 5, most of them stuck with 5. There is some cluster at 6, but demand of 7 stuck with 7. And interestingly, 9 stuck with 9, even though it seems like a very high offer. And there were very, very few unsuccessful demands in part 2. And so here, again, you can see there might have been conflict by the new inexperienced responders, but the proposers knew what they were doing by that point. So the conflict had taught them. You do see more conflict in the reverse roles. This, again, is part 1. You can see these are largely the same, so I'm just going to look at them quickly. And the reverse roles for part 2. These people are still learning. These are new in part 2. Again, these are inexperienced responders who become proposers, and they're making demands, but you can see they're not as strictly near the Nash equilibrium as the other group. And so you do see much more in the way of unsuccessful demands in part 2 for the reverse roles. And that highlighted part of our concern with the large amount of conflict that we saw, and satisfied us that they were using it appropriately. So in conclusion, our adaptation to the ultimatum game builds on previous work with the intent of looking at this to explore Ken Benmore's ideas. And what we did in the game was use experience, role reversal, and competition, or in particular conflict. Similar to the other adaptations, we find proposals that are closer to the subgame perfect Nash equilibria predictions, and we find that proposers have in fact learned how to play like a gamesman. Responders have larger than predicted tendency to engage in mutually costly conflict, even after experience with both roles, but the conflict is instrumental in moving the demands towards the subgame perfect Nash equilibrium. So altogether, we argue that this version of the ultimatum game and the results correspond with Benmore's ideas that fair behavior can be a useful strategy in some cases, but is not likely to be used in others. Thank you.
Yeah, so thank you very much.
Okay.
Oh, Gary,
Yeah.
I'd like to moderate a kind of discussion, and I stop the recording now.
Cool.